In this lecture, we will discuss an introduction to DOE and replicated two-level designs. Let's look at the agenda. In terms of the agenda, we will first go through replicated two-level designs and supplement that with an example. Here are some definitions for some terms that will be used with experimental design. Factors are the input variables, and their levels are the values that these factors will take on. A treatment combination is a combination of factor levels that are of interest. An experimental unit is the object in which the treatment is applied. For example, in clinical trials, the experimental units are people. This is a special case of the general factorial design. These designs all have k variables each at two levels. These levels are called low and high. The design is considered replicated because the entire experiment is run more than one time. Here's the basic checklist for analyzing a factorial design. First, estimate the main effects and interaction effects. Then, formulate a model. If the design is replicated, you can use the full model. If it's unreplicated, a normal probability plot may be helpful. Finally, refine the model, analyze residuals, and interpret the results. The following are a few of the reasons why this type of design is very popular. The fact that they require a small number of runs is beneficial since one can get all of the required information with a small expenditure of resources. Another reason is that the analysis of these designs is quite simple and straightforward. Typically, good experimentation is sequential in nature, which means that you usually will not reach your goal with one experiment. These types of designs allow you to determine the most promising direction to continue experimenting in. Let's motivate this material with an example. This is a chemical example, where factor A is reactant concentration, and factor B is the amount of catalyst. The response here is the percent of recovery. Notice that we have n equals 3 replicates of each 4 treatment combinations, which leads to n equals 12 total runs. The simplest type of 2 to the power of k design is one with 2 factors, which is a 2-squared design. Each factor has k equals 2 levels, and the setup is one where each treatment combination is represented by a corner of a square. Notice that each TC has a combination of plus and. Plus indicates a high level and indicates a low level. In the previous experiment, the treatment combinations are presented in a special order. A gentleman by the name of Frank Yates came up with an order, which we refer to as Yates' order or standard order, to which we can write out all of these designs. The order is found by utilizing letters to represent which factors have a plus sign for that run. Then the letters are put in alphabetical order. Since Yates realized that one treatment combination does not have any plus signs, he labeled that run as L1. Each of the variables on the previous slide was coded as plus, or this is actually short for +1 and -1. All of these variable levels are coded. If we assume that the variables in their natural units are considered CAZs, then the formula on the slide is used to code the variables to the -1 and +1 levels. The question that you should be asking yourself is, what is the benefit of having the levels coded to -1 and +1? The coding given on the previous slide causes the design to become orthogonal. An orthogonal design is one in which all of the inner products of any two columns is 0. The benefit of this is that we are mathematically forcing the covariances between the factors to be 0. This does not mean that the factors are independent, in the purest form. Recall that independence implies 0 covariance, but the reverse does not apply. Another benefit to the -1 +1 coding is that it causes the designs to yield the minimum variance of the estimates on a per observation basis. It also causes the variances of the estimates to be equal. Later on we will talk about something called a half-normal plot, in which this equal variance is critical. Also, the products of columns among these factors are identical to the corresponding interaction columns for factors. No other coding does this. The basic analysis for these designs is quite straightforward. We will first assess the main effects for each factor. This is the difference in the average response at the high and low levels. The main effect of an effect A is just y bar at the high level of a minus y bar at the low level of A. One thing to be aware of here is that we have not taken into consideration the levels of any other factor. This means that we are averaging over the levels of all of the other factors. We assume that the differences are the same at all levels of each of the other factors. Here are the results for the chemical experiment. The main effect for A is 8.34 and for B is minus 5.0. What does this tell us about each factor as it relates to the overall average? Well, for factor A, it tells us that as we change levels of factor A, the average response increases by 8.34. For factor B, the average response decreases by 5.0. This plot is called a main effects plot. It is a way for us to visualize what the main effects are. You can see from the plot for factor A, as we change the level from low to high, we see that the average response increases, and vice versa for factor B. You can get an idea of how important a factor is by assessing the slope of these lines. If the line is horizontal, then most likely the change in the factor level is having little or no effect on the mean response. Recall that for factorial experiments, there are some treatment combinations where the factor levels are changed simultaneously. There is another type of design called a one factor at a time experiment. This design is one where one factor is varied and the remaining factors are held constant. Effects can only be estimated under the assumption that the other factors are held fixed. We would assume that the effect does not change at different levels of the other factors, which is considered to be an additive effect. This means that for this method to be valid, we would need to assume that there is not an interaction present. Since we don't want to make that kind of assumption, we need to calculate the interaction effect. It is very important for you to realize that if there is an interaction present, then you shouldn't just average over the other levels of the other factors. This means that it is the interaction plots that you should be looking at, not the main effect plots. Let's visualize this. Interactions occur when variables act together to impact the output of the process. Interactions plots are constructed by plotting both variables together on the same graph. They take the form of this graph. Note the relationship between variable A and Y changes as the level of variable B changes. When B is at its high, plus, level, variable A has almost no effect on Y. When B is at its low, level, A has a strong effect on Y. The feature of interactions is non-parallelism between the two lines. Degrees of interaction can be related to non-parallelism, and the more non-parallel the lines are, the stronger the interaction. A common misunderstanding is that the lines must actually cross each other for an interaction to exist, but that's not true. The lines may cross at some level outside of the experimental region, but we really don't know that. Parallel lines show absolutely no interaction and in all likelihood will never cross. Here is the interaction plot for the chemical process example. Based on the plot, I would say that the lines are somewhat non-parallel. But the question is, what degree of non-parallelism is enough? We know that because of natural variation in the data, the lines will never exactly be parallel. Let's look at the interaction effect. To calculate the interaction effect, we can do a similar thing as we did for a main effect. We first find all of the levels for which the interaction is at a plus, and when the interaction is at a minus. Now average each of these, and subtract the minus average from the plus average. The interaction effect isn't as easy to interpret, so we will focus on the interaction plot. For our chemical example, the interaction effect is 1.67. Now, since neither the plots nor the estimated effects take into account any variability, we need to adjust. It is for this reason that we need to start to think about hypothesis testing. First, let's look at the model matrix. To begin to discuss hypothesis testing on the effects, we first need to discuss the design and model matrices. The design matrix is a matrix of the treatment combinations. To create the model matrix, we need to add a column of ones at the beginning and a column for each interaction that is present at the end. The interaction columns are created by multiplying together the columns that make up that interaction. Besides column I, notice that each of the columns in the model matrix has an equal number of pluses and minuses. The inner product of any two columns is 0. You should expect this since the design is orthogonal. Notice also that multiplying any column by I gives you that column back. This should not surprise you since I is equivalent to multiplying a number by 1. Finally, the product of any two columns yields another column in the model matrix. A times B yields AB. Also, utilizing modulus 2 math, AB asterisk BC equals AC. We will revisit the modulus 2 math when we talk about fractional factorials. Now let's move on and talk about some basic analysis. Everyone in this course should realize that assessing an estimate of a parameter alone is just not enough. We also need to assess the variability. In order to do this, we need to find the variance of an effect. We can find the variance of an effect estimate as just the variance of a linear combination of independent random variables. For the 2 to the power of k factorial designs, the variance is given here. You should be able to convince yourself that this is correct for 2 to the power of k designs. Usually we report the standard error of an effect. This is found by taking the square root of the quantity seen here. The problem now is, how do we go about finding S? From your basic statistics class, you should recall that for an ANOVA, we estimate sigma square using the mean square error, MSE. Now we just substitute this into the equation for the standard error. Notice that the sums of squares are a function of their corresponding effect. This does not allow for the direct inspection of the effect itself, which of course removes any chance of a practical perspective on the size of the effect. To remedy this, we suggest that you utilize confidence intervals or hypothesis tests. In order to make inference on an effect, we need to get the distribution of the effect estimates. Let's look at the model assumptions. We assume that the errors are independent, have constant variance, and follow a normal distribution. This leads us to the distribution that we are looking for. If we let the true effect for factor be denoted by A, the distribution of the estimate of that effect follows a normal distribution, therefore we can make inference on effect estimates using a t-distribution with DFE degrees of freedom. Of course, you should realize that the reason that we can use a t-distribution to test these hypotheses is because we have only 2 levels for our factors. Another benefit of this is that since the square of a random variable that is from a t-distribution with nu df is equal to a random variable from a f-distribution with 1 in nu df, the t-tests for the effects are equivalent to the f-tests. Now let's look at the hypothesis tests for this case. So we can now build the test statistic in this case as what you see on the slide. Recall that if the true effect is 0, then that factor is not needed in the model. We reject the null when the p-value is less than alpha. Here we need to make sure that we set the type I error before we run the experiment. Why can't we just look at the results then decide on a type I error level? Well, then we could reject everything. We call this data snooping. Now let's look at an example. Here is an example with 3 factors and 2 replicates. You should note that one of the factors is qualitative. Let's look at the experimental results. Here is the design with the response at each TC for both replicates. Let's assess the goal for the study. Since we do not want any cracks, the goal of the experiment is to find the levels of the 3 variables that will minimize crack length. Let's look at the analysis. Here is the effect table. We can see that it gives us the effect and p-value. We should check to see which p-values are less than alpha, which we will assume is 0.05. The ones in bold meet this criteria. We will assume based on the results that the important effects are A, B and AC. Since the p-values are less than alpha, the active effects seem to be A, B, and AC. We will not need the other effects and hence will drop them from the model. Now what happens to the set of 1DF effects that we drop from the model? We will take that information from the non-active effects and pool it into the error. Then we refit the model. We call this reducing our model. When deciding on which terms to keep in the model, we must take into account hierarchy. This means that if any higher order terms are kept, the corresponding lower order terms also should be kept. This is based on the shift principle. This states that if you shift a model based on a constant, then the form of the model should not change. For our example, since AC is active, we need to keep both A and C, even though C is not significant. Let's go back to the alloy example. Let's apply this material to the alloy example using alpha equals 0.05. Here is the reduced model. Notice that all of the p-values are less than 0.05, except for C. This means that those belong in the model and we keep C for hierarchy. So based on the above, it seems that we have a model that seems to have the correct terms in it. What about model assumptions? Earlier we talked about the idea that the errors are independent and identically distributed normal with constant variance. These assumptions need to be checked. We will check this using residuals. Residuals are the difference between the actual observed values and the values that are given by the model, or the mean value of the responses for a given treatment combination. We check the assumptions using residual plots. We would like the residual plots to show no patterns. Beware of trying to find patterns on plots with a small number of points. I would not make any judgment on plot with less than 16 points, and that is pushing it. Each of the plots can be used to check a specific assumption. We will also check assumptions with lack of fit. Lack of fit is a useful concept because it is a way to decide is a reasonable one based on the data. The yellow F component here comes from the terms reduced in the previous model, whereas the pure component comes from the replication of the theses. We can actually create an F-test to see if there is any true LOF. If this test is significant, then we could have terms that were removed that we actually need, or it could be that a higher order model is a better fit. Of course, this is useful if we can actually fit a higher order model. Let's apply this material to the alloy example using alpha equals 0.05. Here are the LOF results. Notice that since the p-value is greater than 0.05, we assume that there is no LOF. Let's check the residual plots. Here we a normal probability plot of the residuals versus fits, residuals versus A and residuals versus B plots. There doesn't seem to be any issues with these. Here is the residual plot for factor C. It seems to be fine as well. So based on the above, it seems that model is adequate and does not exhibit LOF. Now since we have an adequate model, let's return to our goal for the alloy example. The goal was to find the levels of the factors that minimize the response. We will assess this with effect plots. The question is, which plots should we use? It is all based on which effects are significant. If a higher order term is significant, you should read the levels from the higher order effect plot. This is done because we could get the wrong results if we use a lower order term plot instead. So what should we do in this case? Since the main effect B is significant and not involved in a significant higher order interaction, we will use its main effect plot. Based on the plot in the slide, it seems that we should set factor B to the high level. Since interaction AC is significant, we need to get our levels for these two factors from the interaction plot. To minimize the response, we should set factor A to the low level and factor C to the high level. Let's draw conclusions. So to minimize the crack length, we need to set A and B to the low level and C to the high level.